Hey everybody, welcome back to Organic Chemistry. I hope you had a chance to do the problems that I assigned, okay? So these are the problems 1 through 12 that we're going to cover together now. But I really do hope you try them out on your own, okay? There's a lot of learning that we're going to do together through these problems. All right, let's get started. So the first problem here is talking about whether or not things are nucleophiles, electrophiles, or both. In certain conditions, you can actually have something act as both a nucleophile or electrophile. Now, before we begin, I just want to point out that a nucleophile and a base, okay, so something that's looking for a nucleus or a base are similar, okay? They're not the same, they're similar. And an electrophile and an acid are similar to each other. So you could think of them as the same or similar to each other. Why do I say similar? We're not going to worry about that now, but in the next video set, when we learn about SN2, we're going to learn about the difference between a nucleophile and a base, okay? We'll get into more details. But for this problem, you could think of something that donates electrons. That's a base, right? It gives electrons as being either a base or a nucleophile. But here's the thing. So what's the common ground? A base and a nucleophile, they both require lone pair. It doesn't have to be negative. It's better if it is, but it doesn't have to be. So if an atom has a lone pair, it's going to be able to donate electrons. It's going to be a nucleophile. It's looking for the positive, the nucleus. Okay? Now, if something is positive, something is an acid, or it's partial positive, or it's an exception like a group 3 element like boron, then it wants electrons, right? So it's an electrophile. It wants electrons. So let's go ahead and take a look. So for the first one here, we have an atom with lone pairs, right? So that makes this right here a nucleophile. It's going to give electrons to something that needs it. Here it's positive, so it must be an electrophile. Boron is a group 3 atom, right? Or element. That means that boron only has 3 electrons in its outer shell. But remember, it's a Lewis acid. It wants electrons. So this is an electrophile, boron, E. Now, hydrocarbon, think about it. It's not charged. It doesn't have a lone pair, and it doesn't need any electrons. It has already filled completely with H's. So this right here is neither an electrophile or a nucleophile. Hydrocarbon is not, it doesn't do either one of those jobs. So nucleophile is something that wants positive, electrophile is something that wants negative, but if you're completely neutral and there's no charge at all, polarity, then you're neither. This is positive, so what does it need? It needs electrons, so it's an electrophile. This is negative, so it's a nucleophile. This is nitrogen, and you say, well, it's not charged, but it has a lone pair, so it must be a nucleophile. Bromine, that's a anion, a bromoanion, that's a nucleophile. It's got an extra electron, it wants to give it away, right? So it looks for positive. This is negative, so it's a nucleophile. This is oxygen, it's neutral but lone pair, so it's a nucleophile. So if the atom has a lone pair, it's a nucleophile. All right, now for this one here, this is an interesting story, right? Because we learned that the carbon of a carbonyl wants electrons, right? This is an electrophile. It wants electrons. Remember how we connect carbons together in that reaction that we talked about from the synthesis stuff? Well, the carbon can accept electrons, so it's an electrophile. But the oxygen, or this double bond, that can give electrons, so it's a nucleophile. So you have the ability in this one to be both. It could sometimes be a nucleophile, and other times it could be an electrophile. It depends on the circumstances. So in this case, it's both. It depends on what's in the environment. If there's positive in the environment, it'll act as a nucleophile. If there's negative in the environment, it'll act as an electrophile. Okay, so that acts as both. Now the key is you need a polarity. So double bond O is polarity. But double bond carbons, there's no polarity. In this case, it's not going to act as both, but it does have electrons. Double bond and triple bonds can give electrons. They have rich electron source. They have this pi system of electrons. So these right here are nucleophiles. This is a nucleophile. It can give electrons to something that needs them. And the same thing for a triple bond. This is a nucleophile. Look at the one I skipped. That's negative. So that's a nucleophile, right? It wants positive. Okay, now the triple bond is just like a double bond. If it's triple bond to an atom or double bond to an atom that's more electronegative than carbon, then it could do both. But if it's a carbon that it's double or triple bonded to, then it can only act as a donating source. It can give electrons, so it's a nucleophile. Okay, this right here is negative, nucleophile. So let me make sure this is clear. If I have a double bond O, double bond N, double bond S, double bond carbon, then these right here are both nucleophile and electrophile because there's a positive source, carbon, and there's a negative area, oxygen, nitrogen, or sulfur, right? Whereas this is only a nucleophile, only. Because there is no charge, there's no polarity here. So you can't act as both, you have to act as one, just a nucleophile. Because the double bond can give electrons to something. Okay, same thing with a triple bond. Okay, and as far as which one's a better nucleophile, double bond O, N, or S, that's what we're going to learn about in SN2. We're going to figure out which one of these is actually better when we do SN2. All right, the next one is about entropy. Remember, entropy is the amount of disorder, right? This is the amount of disorder. We want to increase disorder. And the way we do that is to have more molecules rather than less. So if you increase the amount of molecules, you're going to increase your disorder in the system. But if you reduce the amount of molecules, you increase the order. You make things more organized. Okay? So let's take a look. In this case, we have A and B becoming C. So 2 becoming 1. That's organizing, right? You're taking things that are having more randomness, more molecules to begin, and making it consolidated. That's not good. So this is going to have a decrease in entropy. There's going to be more order for A. More order. You're decreasing the entropy. All right, look here. You have A and B becoming C. Once again, 2 becoming 1. So you're going to have a decrease in entropy. You're going to reduce the entropy. You're going to make it more organized, more ordered. Okay. Here we have A and B. Remember, whatever's over the arrow is like the same as being next to it on the left. Here's C and D. So you're going with 2 and you're ending with 2. So this has an effect of no change in your order or disorder. It's the same amount to begin as it is to end. Okay. Here you have A becoming B and C. So one thing is breaking up into 2. So this is going to be an increase in entropy. There's more disorder at the end than where you began. The last 2 are tricky. And I have to say, so for E and F, very tricky. But I want to bring it up now, and I don't think that this would come up during this exam. But I want to just kind of give you the idea. Now, when you see this right here, it looks like A is becoming B. It looks like it should be equal, right? There's the same amount of order or disorder from beginning to end. But it actually isn't true. See, here's the thing. When you have a ring that becomes an open system, as soon as a ring opens up into a straight chain, when you open up a ring, now it can rotate around. Remember, rings don't have that much rotation. So there's more disorder. There's more capability of randomness. Remember, disorder, randomness, the same. So when a ring opens up, it then has full rotation, has more randomness in its, configuration. And so by opening up a ring, you actually increase the amount of disorder. You increase the entropy. So this is an increase. So just remember that when you take a closed ring system and open it, you're making an increase in entropy. But if you do the opposite, so here's a open, these chains on the outside, all of a sudden it's closing into a different size ring. Notice that right here, this alkene here is connected single bond to the ring. So it can rotate through the single bond. But once it connects over here, there's no rotation. Everything is now locked into the ring system, and the only thing sticking out of the ring is a double bond carbon. There's no rotation. So this went from open to a closed ring system. So this is a decrease in entropy. Okay, so again, this was tricky. I have to admit, the last 2 problems are not common problems for this exam, but I do want to kind of give you the sense of how to look a little deeper if you had to, okay? So hopefully that's clear.